Hi professors, this video is ECE 492 Hardware Team's design review presentation. Our project is aerial soccer game with blimps, and we are focused on the actuation and control of the blimps. Our hardware team includes Eric is our project manager, and Jose, Romani, Kyle, Will, and me, Yuhang. The purpose of our project is to design long-endurance, lighter-than-air, unmanned aerial vehicles with specialized modular features, such as pushing, grabbing, or blocking abilities. And then we can play the soccer game in the air. To achieve our purpose, there are some requirements for us. The first, our blimp should be able to run in the air about 1 hour with approximately 200 to 220 grams of hardware parts. And second, our blimps need specialized features for offense and defense abilities. The third, our blimps should be modular for different features, like the offense, defense, and the power system, so we can easily assemble, disassemble, and store them.
So here's our design architecture, level 0. It's a very basic design. Has a user input, power on and off, sensor signals going in, as well as electric power. And in the box there's a system initialization, distance and vision sensing, compute sensor data, and motor control. Thus goes and gets the output as desired. So breaking that down, our user input and power on and off are going to system initialization. Once it's initialized, its sensors are on, and you have sensor signals going to distance and vision sensing. That also has electric power given into it because it needs that to run. Distance and vision data then goes from there to compute sensor data, and with computing that sensor data, then you have motor on and off and direction. That goes into motor control as well as electric power that gets you to desired output, which is different for offense and defense. So level 2, distance and vision sensing. The sensor's turned on, so it turns to sensor power, which is given with electric power. Sensor signals, and their sensor power goes to the sensor detects distance sensing and vision sensing. Thus, those have data, and then they go to the compute sensor data section, which then interpret the data to find an objective. Once it has that, then it moves to detection of the object, which the object in this case mainly will probably be the ball, especially for offense it will be the ball. Defense, it's either going to be the ball, the hoop, or an offensive like opponent blimp. So once you detect that motor on and off and direction, then it does that. Motor control, so once you have the motor on and off and direction, you provide motor power and you're given electric power. So it's ready to move vertically or horizontally, so it can move either up and down, to find its objective. So it goes to the output, which the output is the objective. So for offenses, get the ball, score. Defenses, stop the scoring. Offensive blimp design. So this is our basic offensive blimp design, where it has a bracket and it needs an adhesive and a mounting bracket to hold it. So seen to the left is our basic design with 3 prongs, and then the bracket below is seen. So we need an adhesive, so then the ball will not just run away from our offensive blimp since it's neutrally buoyant. We need to have some way to stop it because it acts like an elastic collision once we would hit it with our blimp. So we need some adhesive to be able to stick it to the bracket, so then we're allowed to maneuver and control the ball to score. With that being said, here's our blimp behavior, so offensive state diagram. So you start, you power it on, you configure. Once that's done, you hold. So you're holding to have user input for right now. So you either go forward, back, you can control the yaw, altitude, and speed control. So basically all these are saying where do we want to go and how fast, basically. Once that's done, you find the ball. So once you find the ball, you're going to control the ball and maintain it. So if you ever lose the ball, you have to go back to finding the ball, and once you get that, ultimately control the ball and maintain it. So once you have that, you find the hoop and you score. So if we end up scoring, then you go back to hold, which then resets And then if at any given point we need to end the game, we have the game over. So then if it's equal to 60 minutes, or we need to stop it for, let's say, one of the blimps on fire or something like that, we can power it off and go back to the start. So then everything will shut down and be in one piece. The activity diagram is shown as well, which is very similar to what we just went over in the state diagram. So that's it. Thank you.
Hello, this is Eric. I will continue with the design considerations for our main defense idea. Here, we are mainly adding a net that spans the 54-inch length of the blimp, and it's kept straight by 2 carbon fiber rods, as can be seen in the picture on the right. Improvements from the previous prototype include decreasing the weight and therefore increasing the efficiency. The net only needs to have a downward depth of 18 inches to cover the 38-inch diameter goal, if we also consider the height of the blimp. We are also increasing the mesh opening size and therefore decreasing the material used. Accounting for the deformation of the net and stretch of the material, the largest openings we can have are 11.5 inches at the side. Our current net has an opening size of 4 inches, so this should decrease the weight by half if we don't count the carbon fiber rods. On the next slide, we compare the possible materials for the net. The table compares the specific gravity of the materials. Specific gravity is the ratio of materials density with that of water, which is 1. The lower the specific gravity, the lower the density, and therefore the lower the weight. We see that the highlighted material we chose, polypropylene, has a specific gravity of 0.91, which is the least dense at 0.91 grams per cubic centimeter. We plan to continue to use this material and make custom nets with 11.5-inch openings. On the next slide, we see the intended behavior of our defensive blimp. We have a state diagram on the left and an activity diagram following UML on the right. Both essentially show that the blimp will go to the hoop and stay there for the whole game. By the sheer size of the blimp in the net, it should be able to block the ball. On the next slide, we cover the design considerations for the ballonet system. Through calculations relating the ideal gas law to the buoyant force of air and helium, we found an expression to represent the relationship between the lifting force, the temperature, and the volume of the air in the ballonet. Our goal is to keep the blimp neutral, with weight zeroing the lift force. On the bottom right, we see that we are currently able to inflate the ballonet, and we can also deflate the ballonet. And we have solved most of our sealing issues. But we will be getting a larger balloon to increase the appreciable effect of the ballonet. Also, we're learning to use MATLAB to generate a state space model to simulate the relationships, which will help us program the behavior of our ballonet system. On the next slide, we cover the intended behavior of our ballonet. Again, we have a state diagram on the left and an activity diagram on the right. We intend to have the ballonet keep the blimp neutrally buoyant and prevent the blimp from rising or falling due to temperature.
Hi, this is Romani. I will be doing the part selection conversion chart. First slide here, we have the servo motor conversion chart. We are using the second one in the chart, micro nano servo, 180-degree rotational angle, 3.7 gram. We bought this one in the beginning of the semester because it is precise in movement and it is easy to control over Raspberry Pi or ESP32. But I found out that the next one, which is the last one in the chart here, it has 2.2 grams. So in the future, once we go back to work, we could order this one and start doing prototyping to see how it works. For this slide, we have the battery conversion chart here. We are using the first one. Also, this one we bought it in the beginning of the semester, and it seems like it has a lot of weight than the next one. The next one, it is the last one in the chart. It has only 9 grams, while ours it has 15 grams. So once we go back to work, we can order the next one and start testing it because we can save about 6 grams here. For this slide, we have the ESB conversion chart. We are choosing the first one, ESB32, over the ESB8266 because of a couple of reasons. The first reason here is the weight. Ours has only 9.3 gram, while the ESP 8266 has about 14 gram. We are saving about 4 gram right here. And also because of the ball switch modulation, the one we choose has 16 channel, while the other one has only 8 channel. And more importantly, the GVIO bins, the ESP32 that we choose has 36 bin, and the other one has only 17 bin. So we are having more bin here to use it for like servo motor or other components in the future. For this slide, we have the motor conversion chart. We are using the first one, Bolo DRF, because of a couple reasons as well. The first reason, it is compact on the size, which has only 0.7 multiplied by 0.04, and its weight is really light on weight. It's only 0.5 gram, and we already saving a lot of weight here. And for the most important one is the supply voltage. The one we choose is start between 0 to 11 voltage supply operation, while the other one is start about 4.5 to about 14 gram voltage supply. So the first one we choose it because we are using the Libo battery. It start operating in 3.7 voltage to 6 voltage, so that one fit perfectly here. But if we choose the Adford, it has started operating in 4.5 voltage, so we have to use the both converter supply here, which will result in more weight. Thanks.
Hi, I'm Jose Zurita, and I'll be discussing about our progress with prototyping and hardware. So first we have our prototype 0, which features our most basic electronic components and connections, as well as the programmed ESP32 for Bluetooth control over Blimp. This is built on a prototyping board and is a compact design that uses header pins. Some of the problems with this design are the increase in weight due to the board itself and the header pins, and we are only using through-hole components for this design rather than the surface mount devices. Here we have some pictures of the board with the ESP32 and motor driver mounted onto it. We have a top view, a side view, and a bottom view. We are still working with the Air Swimmer's Shark Blimp, and we were able to measure the load and stall current draw of our motors. So the figure shows our tail motor setup, and the table indicates weight approximations, so you can see that we are working with some weight that can be cut down. Prototype 1 is an improved design of our Prototype 0 using PCB design software, and our design is a 2-layer PCB with proper DRC traces and Gerber files. Some of the problems with this design are that it still only focuses on through-hole components, so the weight problem is still there, and we have some pins, well, many pins left unused. Here we have a top layer and silk screen, as well as a top and bottom 3D view of our PCB. So for prototype number 2, we have made a shift to surface mount devices and started designing proper schematics. At the moment, these schematics are incomplete, however. And some of the problems with this design, well, at least some of the problems we've encountered so far, are that working with SMD components is something brand new to the entire group. So we have some difficulty reading data sheets as well as deciding between different SMD components, such as for voltage regulators. For example, we have simulations for the LTC 3531. LTC 3531 is a linear technology buck boost converter, and using LT-Spice we can simulate some models, and here are two schematics whose only difference is the input voltage. And from the simulation results, we can see that the output voltage is, in both cases, at around 3.3 volts.
Hey, Will here, finishing up the presentation. So, here we have a GIF of our prototype working. So, Jose has put in some work, and here you can see through the Bluetooth controls on his phone, he's able to interact with the onboard ESP32. Yeah, and there you can see the system actuating back back and forth, controlling yaw. Yeah, and we have thrust control. Alright. So, speaking of Bluetooth, just to reiterate again, I'm sure you already know a lot of this, but just for prototyping purposes, we're using Bluetooth because it's easy. But as we move forward with our design, we'll be using the XP3. And I have 2 of these bad boys here, so I'll be further testing these capabilities shown on screen. Bluetooth is nice and all, but the XP3 gives us the range we need. And like I was saying, I'll be doing more testing throughout the rest of the semester to firm up these numbers here. Alright, so with all that information, what are we going to do? So here we have our task laid out. For offense, we'll be finishing up our 3D printing part designs. I'll be testing the limitations of our transceivers, the XPs. Funny enough, we're going to be looking at how to do a basic net weave for our defensive blimp. That should be fun. I was in Boy Scouts. I know some knots, so maybe I'll try my hand at making our own little plastic net. Just the right size, super light. And next up for PCB design, we have our prototype together. Jose did a great job putting it together, and using those lessons, he hopes to make our own custom PCB with some help from Joseph and his expertise. And finally, the Balinet system. We're going to be using our MATLAB simulations to figure out exactly how much work it needs to do, program the behavior of the Balinet system, and last up is to see how well it works in direct sunlight in the presence of, the convection currents. Maybe we can recreate that indoors or in someone's house as best we can. But in the future, we'll be able to test it in a worst case scenario like the engineering building atrium, something like that. And so, timeline. So bear with us here because, certain events are taking place that are not allowing us to get together and follow our normal hardware development timeline. But, so for putting our blimp together, getting everything working, we have our plan laid out for next semester. And here on our Gantt chart, you can see us pretty quickly getting everything together, getting the parts together, making sure they work, developing the power supply, making sure we have the correct endurance, and we can communicate effectively to empower the software team to implement whatever they have concocted. And so right about by week 8, about halfway through the semester, that yields a finished blimp. By then, we'll be partway through testing. As we can see on the next slide, we'll be partway through testing and demonstrating and finishing system integration and well on our way to reporting. And that sums it all up. Thanks for bearing with us. We look forward to hearing your feedback, and thanks for your patience. Bye.